Hello, and welcome to the lecture on 10.7. Today we're going to talk about partial fraction decomposition. I want to start with recall. When adding fractions or rational functions, we find a common denominator first. In this section, we want to decompose a rational expression into a sum of its parts. What we're saying here is that instead of adding two fractions together by finding a common denominator, we want to take a single fraction and pull it apart into its different, fractions with different denominators. Now there's four different cases that we're going to go over. The first one being distinct linear factors. Each of these cases is going to involve the denominator of the rational expression. So this first case is distinct linear factors. If our denominator is a bunch of distinct linear factors, then we fall into case one. The denominator is a product of distinct linear factors. Suppose that we can factor q of x as q of x is equal to a1x plus b1, a2x plus b2, all the way up to a sub nx plus b sub n, with no factor repeated. In this case, the partial fraction decomposition of p of x divided by q of x takes the form p of x over q of x is equal to a1 over a1x plus b1 plus a2 over a2x plus b2, all the way up to a sub n over a sub nx plus b sub n. So basically what we're doing is we're taking apart the denominator. So our q of x can be written as a bunch of linear factors. If you've forgotten what a linear factor is, it has a single exponent. It has an exponent of, our x variable has an exponent of 1. We have a sub 1x plus b sub 1, a sub 2x plus b sub 2, all the way up to a sub nx plus b sub n. These are the n linear factors. Now we take each of these and we put it under a separate fraction. And we put a number on top. Now here, a sub 1, a sub 2, all the way up to a sub n, these are constants. These numbers, or these values, need to be 1 degree less than the denominator, and this will be important when we move forward into the other cases. But for right now, because the degree of the denominator is 1, the degree of each of these numerators has to be 0, i.e. they are just constants. What we're going to do next is we're going to end up finding the value of a1, a2, all the way up to an. And I think it'll be easier to show it in an example. Find the partial fraction decomposition. Suppose that we have f of x is equal to 7x minus 3 divided by x cubed plus 2x squared minus 3x. Now this is in the form of p of x divided by q of x, where q of x and p of x are both polynomials. We want to first factor the denominator, and then we'll decompose it. So factoring out an x will give us 7x minus 3 divided by x times x squared plus 2x minus 3. We now need to factor x squared plus 2x minus 3. We look for two numbers that multiply to negative 3 and add to 2. Those two numbers are going to be 3 and negative 1. So our function then becomes 7x minus 3 divided by x times x plus 3 times x minus 1. Notice that we have linear factors. X plus 3, x minus 1, all fit this form. Where a1 is 1 and b1 is 0. A sub 2 for x plus 3, a sub 2 would be 1 and b sub 2 would be 3. And for x minus 1, a sub n in this case, but a sub 3 would be 1 and b sub 3 would be negative 1. Okay, so what we want to do next is we want to set this equal to its decomposition, where we have constants on top and then our respective factors on the bottom. So this will equal, rewrite this, 7x minus 3 divided by x times x plus 3, x minus 1. This can equal a divided by x plus b divided by x plus 3 plus c divided by x minus 1. Notice each of them have their own fraction. Now what we want to do is we want to solve for a, b, and c. A, b, and c are just going to be constant numbers. They're fixed, they're not changing. But we can do this by setting up a system of equations. And this is the long way. There is a shortcut that I'll show you after I do the long way. The shortcut really works well for linear factors, but it doesn't work well in higher ordered terms. So what we want to do now is we want to multiply both sides by this, by the first denominator that we have, x times x plus 3 times x minus 1. Because when we multiply this side, this entire denominator will need to distribute to each of these. So we'll have x times x plus 3 times x minus 1. And then upon distribution, we're going to get some cancellations. So when we distribute this to each of these, we're going to end up with a, where the x cancels, but we still have the x plus 3 and the x minus 1. So we have a times x plus 3 times x minus 1 plus b. Now in this term, the x plus 3 cancels, and we're left with x and x minus 1. And then when we multiply to the c term, the x minus 1 cancels, and we're left with x times x plus 3. So c times x plus 3. So this is all equal to the left side. Now on the left side, we multiplied by the denominator. So this denominator will cancel with what we multiplied by. And we're left with just 7x minus 3. All right, now, remember when we have a system of equations, each equation is usually related to something. They have something in common. And that thing in common is going to be the degree of the x variable. And remember, x to the 0 power is just a constant. I'm just writing it like this so that we can stay within our pattern. So let me go ahead and multiply this side out first a little bit, just so that we can see things a little bit more clearly. This will become x squared plus 2x minus 3. So we'll have a times x squared plus 2x minus 3, which is right here. Remember, that's how we factored. Plus bx squared minus bx plus cx squared plus c times 3x. And we can just rewrite this as 3cx. Right now, if I distribute my a, then I have an ax squared plus 2ax minus 3a. Because this, remember, needs to distribute to each of these terms. Now again, remember that a, b, and c are fixed. They're actual numbers. They're holding the place of numbers that we're looking for. So on the left side, we have something is equal to something on the right side. And on the right side, so we have ax squared plus bx squared plus cx squared. So in total, we have a plus b plus c total x squareds. Keep in mind that this would be ax squared plus 2ax minus 3a. So I'm going to underline the terms that we used. We used this one, and this one. And if you factor out the x squared, you get this. Now, how many x squareds do I have on the left? Oh, it doesn't show any x squareds, but that just means that we have 0 of them. So on the left side of the equation, of this equation, we would have 0 x squareds. So notice that if I have 0 x squareds on the left, and I have this many x squareds on the right, these coefficients need to match. Otherwise, we don't have equality. But we know that these two things are equal because we have an equal sign. Now, how many x terms do I have on the left? I have 7 x terms on the left, x to the first powers. So 7x is going to equal, how many x terms do I have on the right? 2ax minus bx plus 3cx. So that would be this term, and this term. And again, you factor out the x. So I would end up with 2a minus b plus 3c. Total x values. Again, think of this all as a number. It's an expression, sure, 2a minus b plus c, but that will give us some number. And this number is the total number of x's that I have on the right. The total number of x's I have on the left is 7. So this equation will be the same thing as 2a minus b plus 3c is equal to 7. Just like up here, a plus b plus c is equal to 0. And if we do the same thing with constants, we can see that we have no c constant nor b constant, but we do have a negative 3a constant on the right. Now on the left, we have a negative 3 x to the 0 power, which again is 1. Remember, x to the 0 power is just 1. I'm just indicating that this is a constant value. And this is equal to negative 3a x to the 0 power. Again, indicating that this is a constant. So the number of x to the 0 powers on the left has to match the number of x to the 0 powers on the right, and that is negative 3 equals negative 3a. So my equations become 0 is equal to a plus b plus c, 7 is equal to 2a minus b plus 3c, and negative 3 is equal to negative 3a. Now I have my system of equations set up. I just need to solve it. Once I solve it, then I know what my a, b, and c are, and I can plug them in to give myself my partial fraction decomposition. Well, this third equation is pretty easy. We just divide by negative 3. We get a is equal to 1. Now I have equations 1 and 2, and I know that a is equal to 1. So I can plug that in. So equation 1, such that a is equal to 1, gives me 0 is equal to 1 plus b plus c, or b plus c is equal to negative 1. Similarly, for equation 2, such that a is equal to 1, gives me 7 is equal to 2 times 1 minus b plus 3c, or negative b plus 3c is equal to 5. Now I have two equations and two unknowns. I just need to figure out my b and my c. And this one is pretty straightforward. If I just add the two equations, my b will cancel, and I'm using the elimination method in this case. So adding my equation 1 such that a is equal to 1 and equation 2 such that a is equal to 1, I would get 0 plus 4c is equal to 4, which means c is equal to 1. So we know what c is, and we know what a is. So I could plug it into any of these equations. Go back to equation 1 such that a is equal to 1, c is equal to 1, and we get that b would be negative 2. 0 is equal to 1 plus b plus 1. And we end up with b is equal to negative 2, as I stated. Now, I do want to make a point here, because not everyone will divide up their a, b, and c in the same way that I did. What's important is the end result. What's important is that 7x minus 3 divided by x times x plus 3 times x minus 1 is equal to whatever my a value is, 1, divided by x, plus whatever my b value is, negative 2, divided by x plus 3, plus whatever my c value is, 1 divided by x minus 1. So if you had your b over your x minus 1 instead of your c, then your b will turn out to be 1 and your c will turn out to be negative 2 instead. So all that matters is that this rational expression decomposes into this expression with my 1 divided by x, negative 2 divided by x plus 3, and 1 divided by x minus 1. Okay, let's go ahead and do the shortcut just to show you how this is done with a little bit of a shorter method. Again, the shortcut works when you have linear factors in your denominator. It doesn't always work, so you have to be careful on when you apply it. So if we go back to this line right here, before we multiply everything out, we have a times x plus 3 times x minus 1 plus bx times x minus 1 plus cx times x plus 3 is equal to 7x minus 3. Then we have this 7x minus 3 is equal to a times x plus 3 times x minus 1 plus bx times x minus 1 plus cx times x plus 3. This one here. Now, remember that x is our variable. So as x changes, that's what's changing our y value for this particular expression. Right? Now, this needs to equal this for every x value, for every single x value, not just for 1, not just for 2, for every single x value. That means that it has to work for specific x values as well, because every x value is included in that equality. I can say that x equals 1 is going to be included in the equality also. So if I let x equals 1, then I can figure out an equation for both sides. I can figure out an equation that's easier to solve. So if, let's say that we let x equal 1. Then the equation that we get is 7 minus 3 is equal to a times 4 times 0 plus b times 1 times 0 plus c times 1 times 4. Notice that my a term will drop out because I have this 0. A times 4 times 0 is 0. My b term will drop out as well. B times 1 times 0 is 0. So these two terms drop, and that's what we really wanted. That's why we choose x equals 1, because I know that it'll drop my a term and my b term. So c times 4 is going to equal 4. So I have 4 is equal to 4c, which means that c is equal to 1. Now, this is not the only x value for which this equation needs to be true. It needs to be true for every x value. So let's choose another one. Which one do you think we should choose next? Let x equal negative 3. You could also have chosen 0. Both of those are fine solutions. I'm going to choose negative 3 so that my a term drops and my c term drops. And if x is negative 3, then I get 7 times negative 3 minus 3 is equal to a times 0 times negative 4 plus b times negative 3 times negative 4 plus c times negative 3 times 0. And again, my a will drop and my c will drop because they're being multiplied by 0. So all that I have left is 12b on the right. All I have left on the left is a negative 24. 7 times negative 3 is negative 21. Negative 21 minus 3 is negative 24. And that will give me what I want. Divide by 12 and we get b is equal to negative 2. Right, now the last one, what do we want to let x be next? Now again, this equation needs to be true for every x value, and that includes when x is equal to 0. So we have 7 times 0 on the left, minus 3, so we have negative 3 on the left. We would have a times 3 times negative 1 plus b times 0 times negative 1 plus c times 0 times 3. And again, b and c drop out because they're multiplying by 0. That's why we choose x equals 0. We end up with negative 3 equals negative 3a, which will then give us a is equal to 1. So our solution is a is 1, b is negative 2, c is 1. And then we can plug that in to our decomposition. 7x minus 3 divided by x times x plus 3 times x minus 1 is equal to 1 divided by x plus a negative 2 divided by x plus 3 plus 1 divided by x minus 1. And this is our solution. Right, try one on the accompanying worksheet. Find the partial fraction decomposition of the rational expression f of x is equal to 12 divided by x squared minus 9. And in the next section, repeated linear factors, we're going to do basically the same thing. Now it's going to be, we're going to have to put a little bit of nuance on it, but it's roughly the same thing. Case 2. The denominator is a product of linear factors, some of which are repeated. Suppose the complete factorization of q of x contains the linear factor ax plus b repeated k times, that is, ax plus b to the kth power, is a factor of q of x. Then, corresponding to each such factor, the partial fraction decomposition for p of x divided by q of x contains a sub 1 divided by ax plus b plus a sub 2 divided by ax plus b squared plus all the way up to a sub k divided by ax plus b to the kth power. So this is a little bit to unpack here. First, when we talk about ax plus b being repeated k times within the factorization of q of x, what we're saying is that ax plus b has a multiplicity k. So it's repeated k times. So this, ax plus b to the kth power, is a factor of q of x. Now, if this is the case, then ax plus b shows up in the factorization k times if we list them all out. And for every time that we have a root that is repeated, then we add this to the corresponding partial fraction decomposition, where we have to account for every single one of those k multiplicities. So notice that we stop at k, because this is repeated exactly k times. Now this would just be for this one root that's repeated k times, and we'd have to do the same thing for every single root that's repeated. Let me show you with an example. Find the partial fraction decomposition for f of x is equal to 25x squared minus 15x minus 14 divided by 3x plus 2 times x squared minus 4x plus 4. Now, first thing you need to do is actually factor this, the second one here, because it factors nicely into x minus 2 squared. So we would have 25x squared minus 15x minus 14 divided by 3x plus 2 times x minus 2 quantity squared. Now notice, x minus 2 is squared, so it appears twice in the factorization of q of x, which would be if we multiplied this entire thing out. It appears twice. So this particular root, x minus 2, is going to be listed twice. Once with a single power and once with a square. So we have 25 x squared minus 15x minus 14 divided by 3x plus 2 times x minus 2 squared. This will equal a divided by 3x plus 2. This is the only one that we list here because it's to the power 1, so we don't need to list this one again. Plus b divided by x minus 2 plus c divided by x minus 2 squared. Now, if you think about it, this denominator is actually x squared minus 4x plus 4. So technically, this denominator actually has degree 2. But whenever we're doing a partial fraction decomposition, we use 1 degree less than what's inside the parentheses on top. So c is 1 degree less than x minus 2. That's why we choose c instead of cx plus d, which we'll do in the next topic. Now here, we need to make sure that we do this in this particular way because we need to account for every possibility. We could have a version of the decomposition that comes up with just something that looks like this. This is possible, absolutely. But it's also possible that we have something like this where it's b divided by x minus 2, where this fraction and this fraction still need to find a common denominator between each other. We would have to multiply this fraction top and bottom by x minus 2 in order to get a common denominator just between these two fractions. And since we would need to do that in order to find a common denominator, we need to list this as part of the partial fraction decomposition. It's very important. Right. Next step, again, multiply by the denominator. So when we multiply both sides by the denominator, we would have 3x plus 2 times x minus 2 squared. 3x plus 2 times x minus 2 squared. Now again, this distributes to each of these. So on the left side, it completely cancels. And we're left with 25x squared minus 15x minus 14. And on the right side, when it distributes, each fraction will cancel some of this multiplier. 3x plus 2 is in the denominator, so it'll cancel with a 3x plus 2 here. So we would have a times x minus 2 squared plus b times, now in b, x minus 2 only cancels once. We have 2 of them here, so it'll only cancel with one of these, and we'll be left with an x minus 2 as well. So we would have 3x plus 2 times x minus 2 plus c times 3x plus 2, and that's it. Notice that we have the x minus 2 squared, so this cancels with this entire term, and all that's left is the 3x plus 2. Right, I'm going to do the long way because I think after the distinct linear roots case, after case 1, I think it's more efficient to just go the long way. That's what I'm going to do here. So you have to multiply everything out. This would be x squared minus 4x plus 4 times a. Plus, here when we multiply out, we would have b times 3x squared plus 2x minus 6x. So it'll be minus 4x overall minus 4. Plus, and this one is 3cx plus 2c. Now we distribute our a and b, and we would have ax squared minus 4ax plus 4a. If you can just do it from here, if you don't need to distribute this, then you can go ahead and go for it. For instance, I know that I have ax squareds because I know that my a needs to be distributed to all 3 of these. So if you can do that in your head while you're listing out your equations for your system of equations, then go ahead and do that. But for many students, they like to list this all out, so I am going to go ahead and go through that. Plus 3cx plus 2c. Now on the left, we still have 25x squared minus 15x minus 14 because we haven't changed anything yet. Now we list our equations. Equation 1 will be correlated with the x squared term, because that's the highest degree that I have, just an x squared. Equation 2 will be correlated with x to the first power, and equation 3 will be x to the 0 power, which is the same thing as just the constant term. So if it doesn't have an x attached to it, then that's going to go in this equation. So on the left, I have 25 of the object x squared. Notice I have 25 of them. On the right, I have a plus 3b, and that's it. There's no cx squared. So this will equal a plus 3b. And I'm using this term and this term. Since equality holds, the number of x squared terms needs to match the number of x squared terms. The number of x terms needs to match the number of x terms, and the constant needs to match the constant. So now let's look at our x term. We have negative 15 on the left, negative 15 x's. On the right, I have a negative 4a minus 4b plus 3c. That's how many x terms I have, because those are all attached to an x. And then for the constant term, my constant on the left is negative 14. My constant on the right will be the sum of 4a minus 4b plus 2c. 4a minus 4b plus 2c. I call this equation 1, this equation 2, and this equation 3. Okay. Now, if you want to put these into a matrix and solve the linear system by using Gaussian elimination, absolutely, that's fine. I'm just going to go through the traditional system of equations. Now here, equation 1 doesn't have a c term. And since it doesn't have a c term, if I can eliminate my c between equation 2 and 3, then I would have two equations with two unknowns, namely a and b. So what I'm going to do first is take equation 3 and I'm going to divide it by 2. Notice that every single constant is divisible by 2. So equation 3 will be the same thing as negative 7 equals 2a minus 2b plus c. Now I want to eliminate my c. So I'm going to use equation 2 and equation 3 in order to eliminate c. Specifically, I'm going to rewrite this as equation 4, but it'll be 3 times equation 3 minus equation 2. So I'm going to take this equation, multiply it by 3, and then subtract this equation. 3 times negative 7 is negative 21. Negative 21 minus a negative 15, same thing as adding 15. We'll have negative 21 minus a negative 15 is going to be negative 6. We have a negative 6 on the left. And then on the right, again, I'm multiplying equation 3 by 3, so this will be 6a minus a negative 4a will equal 10a. Negative 6b minus negative 4b. Negative 2b. And that should be it. 3c minus 3c will be 0. So I have equation 4 and equation 1. Equation 1 is 25 is equal to a plus 3b. Now I simply need to figure out what b is, or a is, and then I can solve for the other variable in this equation. I'm going to divide equation 4 by 2. Again, each of these is even. So equation 4 will become negative 3 equals 5a minus b. Now I do equation 1 plus 3 equation 4. 3 times equation 4. So that I can eliminate my b. So equation 1, 25 plus 3 times equation 4. So 25 plus 3 times negative 3. 3 times negative 3 is negative 9. 25 plus negative 9 is 16. A single A, plus 3 times 5A. 3 times 5A is 15, plus A is 16. So we have 16A. 3B plus 3 times negative B. Negative B times 3 is negative 3B, and 3B plus a negative 3B is 0. So I end up with 16A equals 16. So A equals 1. We divide by 16. Since I know what A is, I can go back to equation 1 and substitute A equals 1. And I'll have 25 is equal to 1 plus 3B. Subtract the 1, I have 24 is equal to 3B. And then divide by 3 and I get B is equal to 8. Now I'm going to use this equation 3 in order to solve for C. Since C has a coefficient of 1 here, I think it's the easiest. We take equation 3, substitute A and B. A equals 1, B equals 8. We would have negative 7 equal to 2 times 1 minus 2 times 8 plus C. So negative 7 is equal to, this is negative 16 plus 2 is negative 14. And if we add the 14 over, we have C is equal to 7. So this is my solution. A is equal to 1, B is equal to 8, C is equal to 7. So we're going to have 1 divided by 3x plus 2, 8 divided by x minus 2, and 7 divided by x minus 2 quantity squared. That's how this expression breaks down as into its partial fraction decomposition. So we would have 1 divided by 3x plus 2 plus 8 divided by x minus 2 plus 7 divided by x minus 2 squared. And that is 25x squared minus 15x minus 14 divided by 3x plus 2 times x minus 2 quantity squared. That's how it breaks down. My solution, my final solution is this. The partial fraction decomposition of this expression. Now I will note that some of the problems turn out to be very, very ugly, where you get really ugly fractions on these. You would just plug it in like I am with my 1, 8, and 7 here. Say A is equal to 15 divided by 31. You would just plug in 15 divided by 31 for A and leave it in the numerator. Now it can simplify a little bit. You can push the 31 into the denominator if it was that, but you don't need to. You just leave it as a fraction in the numerator. It's the same exact value. It's just a different way of looking at it is all. All right, the next topic I want to talk about is irreducible quadratic factors. The quadratic is irreducible if it can't be factored using real numbers. So in this context, we're not talking about being able to factor using complex numbers, just real numbers. It's irreducible if you can't factor the quadratic using real numbers. This brings us to case 3. The denominator has irreducible quadratic factors, none of which are repeated. Suppose the complete factorization of q of x contains the quadratic factor ax squared plus bx plus c, which cannot be factored further. Then, corresponding to this, the partial fraction decomposition of p of x divided by q of x will have the term of the form ax plus b divided by ax squared plus bx plus c. So just like the last case, we're talking about just this term corresponding to this particular factor. The rest of the Partial fraction decomposition will follow the rules of the previous cases. So here, if we have a quadratic that cannot be reduced, so we cannot factor it, then we need a term that has an ax plus b in the numerator. Now, remember, we need to account for every possibility, and it is possible for us to have an x term in the numerator since the denominator in this case is x squared. We have a degree 2 denominator, therefore we need to account for the possibility of having a degree 1 numerator. Now this still is irreducible. We still can't reduce this fraction because the numerator is a degree that's less than the denominator. So for instance, if we had something where, let's say we had a fraction, p of x, and then in the denominator we had ax squared plus bx plus c, and then dx squared plus ex plus f, also in the denominator. Our partial fraction decomposition would be ax plus b over ax squared plus bx plus c, plus cx plus d divided by dx squared plus ex plus f. Now with these types of problems, doing the shortcut is a little bit difficult because we have this x in the numerator makes things difficult. So I would recommend doing it the long way like we did the last problem. Again, the shortcut is really good for case 1, but cases 2 through 4, it's not as good for. Find the partial fraction decomposition, where our function is x cubed plus 13x squared plus 10x plus 22 divided by x squared plus x plus 2 times x squared plus 1. Now, neither of these quadratics are actually reducible. So we're going to end up with just 2 terms in our decomposition. X cubed plus 13x squared plus 10x plus 22 divided by x squared plus x plus 2 times x squared plus 1 will equal, now remember, it needs to be 1 degree less than the denominator. Since our denominator in this case is going to be x squared plus x plus 2, we need an x term in the numerator to account for that possibility, ax plus b. And then we have an x squared plus 1 in the denominator. And again, the degree in the denominator is 2, so we need to account for the possibility of having a degree 1 numerator. So we would have cx plus d. Now we solve these problems very much the same way, where we're going to solve for a, b, c, and d using a system of equations. I cannot emphasize enough, the degree of the numerator needs to be 1 degree less than the denominator whenever you do your decomposition and start the problem like this. So just like before, we multiply by the denominator. So we multiply by x squared plus x plus 2, x squared plus x plus 2, and x squared plus 1. Now again, this is going to distribute. And when we distribute to this term, the x squared plus x plus 2 will cancel, and we'll just have x squared plus 1 times ax plus b. And then when we distribute to this term, the x squared plus 1 will cancel, and we'll be just left with cx plus d times x squared plus x plus 2. So we have, on the left, x cubed. So we have on the left, x cubed plus 13x squared plus 10x plus 22. And on the right, we have ax plus b times x squared plus 1 plus cx plus d times x squared plus x plus 2. Now, as I said before, whenever we're doing these problems, the shortcut method is actually kind of tricky. If you don't get really good values, then it's kind of hard to actually solve them. It makes it no more efficient than just doing it the regular way. Especially when we have these squared terms in the denominator. When we have the squared terms in the denominator, you'll see the system of linear equations is actually not too bad. We multiply everything out. We're going to FOIL. So we have the first times the first, the outer, the inner, and the last. And we have ax cubed plus ax plus bx squared plus b. Here we do the same thing, except we now have to multiply each term by each term. So cx needs to multiply by x squared, x, and 2. Just like d needs to multiply by x squared, x, and 2. So we have cx cubed plus cx squared plus 2cx plus dx squared plus dx plus 2d. And on the left, we didn't change anything, so we have x cubed plus 13x squared plus 10x plus 22. Okay, now we write out our system of equations. Now each equation in this case are going to correspond to x cubed because we have x cubed terms now. X squared, x to the first power, and x to the 0 power, which again, this is the constant term. The number of x cubeds on the left needs to match the number of x cubed terms on the right. Now on the right we have a x cubed here and c x cubed here. There's no other x cubes. So we have a plus c total x cubed terms. So on the right we would just have a plus c. On the left we have 1 because we only have one x cubed here. So we would get 1 is equal to a plus c. Do the same thing for your x squared terms. Here there's no ax squared. We have a bx squared, a cx squared, and a dx squared. And on the left we have 13 total x squareds. So we have 13 on the left is equal to b plus c plus d. And that's from here, here, and here. I'm going to underline them so that we know that we used them. The number of x terms on the left needs to match the number of x terms on the right. We have 10 x's on the left. We have ax here, 2cx here, and a dx. So on the left, we have 10. And on the right, we have a plus 2c plus d. A, 2cx, dx. So we used those terms now. And then lastly, the constant term. We have 22 ones on the left, and we have b plus 2d ones on the right. Ones being basically our constant. So 22 is our constant here, b plus 2d is our constant on the right. So we would have 22 is equal to b plus 2d. And you can see that our system of linear equations is actually pretty sparse. There's a lot of zeros here. There's a lot of missing terms, which is nice. It makes the system a little bit easier to solve. Our end goal is to get to one equation, one unknown. So any way to eliminate variables quicker is very helpful. We can either have one equation, one unknown, two equations, two unknowns, or three equations and three unknowns. Unfortunately, any three equations has four unknowns if we choose any three equations. Like for instance, this one and this one, they have four unknowns, A, B, C, and D. And then each of these have three individually. So we can never group three equations with three unknowns. So instead what we want to do is combine a couple of equations to get two equations and two unknowns. So what I'm going to do is I'm going to eliminate D from all equations. So I'm going to take This process is actually going to be a little bit long. I already have equation 1, which doesn't have a d in it. So I'm just going to rewrite it over here. Equation 1 equals a plus c. Then I'm going to eliminate the d between these two equations, 2 and 3. And we'll do 3 minus 2. We'll call this equation 4, and we'll make it equation 3 minus equation 2. So equation 3 minus equation 2, 10 minus 13 is negative 3. A minus 0 is A. 0 minus B is negative B. 2c minus c is c. And d minus d is 0. So we have no d here. Now, this is really nice. A plus c, so we can actually figure out b pretty easily. For practice, I'm going to get the third equation with 3 unknowns, and I'm going to combine equation 2 and 4 so that I don't add an a in there. Call this equation 5. That will be 2 times equation 2 minus equation 4. I just realized that this should not be equation 4. This should be equation 5, and this one will be equation 6, so that we have unique representatives. 5, we already had an equation 4. No harm done there. So 2 times equation 2. 2 times 13 is 26. 26 minus 22 is 4. 2 times 0 minus 0, so there's no a. 2 times b is 2b minus b is just b. 2 times c minus 0 would be 2c. And then 2 times d minus 2d is 0. Okay. Now we didn't actually need to do this because we can get equation 1. If we use equation 1 and 5, we can eliminate both a and c, and we can just figure out what b is. Let's go ahead and do that. Call this equation 7. This will be equation 1 minus equation 5. 1 minus negative 3 is 4. A minus a is 0. 0 minus negative b is b. And c minus c is 0. So b is equal to 4. Now I have equation 6, which has just b and c, so I can figure out what c is using equation 6. Equation 6 such that b is equal to 4 will be 4 is equal to 4 plus 2c. Subtract by 4, I get 0 is equal to 2c, and c is equal to 0. Now it's okay for a term to be equal to 0. Up here, all that means is that we'll have 0x plus something. So d should be something. It has to be something in this case. Otherwise, we wouldn't get a decomposition. So now that I know b and c, I can figure out what a is using equation 1. Equation 1 such that c is equal to 0 gives me that a is equal to 1. Just plugging in 0 here. So I have 1 equals a. Now that I know a, b, and c, I can use any of these any equation with a d in it in order to solve for d. I'm going to use equation 2 because equation 2 is pretty easy. D is all my terms just have a 1 coefficient. So we'll have a is equal to 1. I don't need, there's no a. B is equal to 4, and c is equal to 0. And we would then have 13 equals 4 plus 0 plus d, which will give us d is equal to 9. See, 1049 is our solution to this system. So if we write this out in the decomposition, we would have a is 1, so 1x plus 4 divided by x squared plus x plus 2 plus 0x plus 9 divided by x squared plus 1. So this would be x plus 4 divided by x squared plus x plus 2 plus 0x plus 9 divided by x squared plus 1. So this would be our decomposition. For this fraction. I want you to try one now on the accompanying worksheet. Echo this process to find the partial fraction decomposition of f of x is equal to 5x squared plus x plus 19 divided by x minus 1 times x squared plus 4. Now I will give you a little bit of a hint here. This x minus 1 is actually pretty easy because it just falls into the very first case. So you're going to only have a divided by x minus 1. Now this one is, again, quadratic. So you need to do 1 degree less. So it'll be bx plus c divided by x squared plus 4. All right, the last topic I want to talk about is repeated irreducible quadratic factors. This brings us to case 4. Now, case 4 is going to be a combination of case 2 and case 3. The denominator has a repeated irreducible quadratic factor. So basically, we take case 3, but we add that is repeated, that quadratic factor is repeated. So basically, we take case 3 and we add that quadratic factor is repeated. Thus, it falls to something like case 2, where we have to repeat it within our partial fraction decomposition. Suppose the complete factorization of q of x contains the factor ax squared plus bx plus c to the k power, where ax squared plus bx plus c can't be factored further, i.e. it's irreducible. Then the partial fraction decomposition of p of x divided by q of x will have the terms a sub 1 x plus b sub 1 divided by ax squared plus bx plus c plus a sub 2 x plus b sub 2 divided by ax squared plus bx plus c squared, and so on, all the way up to a sub k x plus b sub k divided by ax squared plus bx plus c to the k power, just like in case 2. So we have to repeat, just like case 2 where we had these repeated terms in our factorization. Except that now it's quadratic instead of linear, so the numerator is of the form ax plus b. Because again, it has to be 1 degree less than the denominator. Do an example. Find the partial fraction decomposition. So suppose that we have the rational expression 7x cubed plus 5x squared plus 20x plus 17 divided by x squared plus 2 squared. So the decomposition, because this is repeated, this will be listed as x squared plus 2 and then x squared plus 2 quantity squared. Remember that we have to list this as many times as we have a power. So we have 2 as a power, so this factor gets listed twice. One with 1 power and then 1 with a second power. This. And then we have ax plus b, dx plus d. And then the process is identical to all of the other cases. multiply both sides by the denominator, and then solve the system of linear equations. We multiply both sides by x squared plus 2, quantity squared. Again, this distributes to both of these terms. When it distributes here, we're going to be just left with cx plus d, and then when it distributes here, one of the two x squared plus 2's will cancel. So when we multiply on the left, we end up with 7x cubed plus 5x squared plus 20x plus 17. And then on the right, we have ax plus b times, again, when we distribute this, only one will be canceled, so we still have an x squared plus 2 plus, and then cx plus d, because the entire term cancels for the cx plus d term. Let's FOIL this out a little bit. We do our first outer inner last. To multiply it out, we have ax to the third power plus 2ax plus bx squared plus 2b plus cx plus d. Cx plus d just carries down. Okay, now we're ready to set up our system of linear equations. Again, each equation corresponds to the number of each degreed term. Here we need to have 7x cubed on the right. We have 7 on the left, so we need 7 on the right as well. We have 7 on the left. The only x cubed term on the right is this ax cubed. So it's going to just be a is equal to 7. I've used this one, so underline it. Then equation 2 will correspond to the number of x squareds on each side. We have 5x squareds on the left. We need to have 5 on the right. The only x squared term on the right is this bx squared. Underline that to denote that I've used it. And we have b is equal to 5. And we have our x term here. We have 20 x's on the left. We have 2a plus c on the right. 20 is equal to 2a plus c. We underline that. And then our constant, x to the 0 power is the constant, remember. So we have 17 as a constant on the left, which means we need a 17 constant on the right, and that's 2b plus d. Now this system is very, very clearly pretty straightforward. A is equal to 7, b is equal to 5. Those two are immediately solved for. Then I know what a is, so I can solve for c. Call this equation 1, 2, 3, and 4. Equation 3, such that a is equal to 7, gives me 20 is equal to 2 times 7 plus c. This is 14, subtract, and we get 6 is equal to c. We have c is equal to 6 here. And then 4, such that b is equal to 5. So if my b is equal to 5, basically 17 equals 10 plus d. 17 equals 2 times 5 plus d. Subtract over, and we have 7 is equal to d. So d is equal to 7. This is the solution to this system. We just need to plug each of them in to our partial fraction decomposition. 7 for a, 5 for b, 6 for c, and 7 for d. So this will be 7x plus 5 divided by x squared plus 2 plus 6x plus 7 divided by x squared plus 2 quantity squared. But I'm going to do one more example because I want to show you a little bit of how we separate this out using multiple cases. Suppose that we had a function f of x is equal to something with a denominator like x minus 1 times x plus 2 cubed times x squared plus 1 times x squared plus x plus 5. So each of these denominators falls into different cases. I'm not going to write a numerator because it's irrelevant. I just want to show you how this will decompose with our constants in the numerators of each fraction. So first of all, we want to take each of these and separate them into their own fraction in a sum. But furthermore, the ones with repeated roots will need to have multiple versions of this factor. So first of all, let's start with x minus 1. So f of x will look like this, where we have x minus 1 here and an a on top, because this is not a repeated root and it's linear. So we only have a constant in the numerator. Plus, we have another linear factor here, but it's repeated. So we need to write this as many times as we have an exponent. It'll be x plus 2, x plus 2 squared, and x plus 2 cubed under their own fractions. Again, because we need to account for every possibility. These three, even though they look like they have the same denominator, they really don't. This is just x plus 2 squared, and x plus 2 cubed. They are different denominators because I would have to multiply this one top and bottom by x plus 2 squared to get the same denominator as this. And I would still have to multiply this one top and bottom by x plus 2 to get this denominator. So we need to break it up so that we have all of our bases covered. Now, since they are linear, this would still be b, c, and d, just like this, where we have a constant in the numerator and not a linear function. Now we come to the cases where we have irreducible quadratics. X squared plus 1, x squared plus x plus 5. So this one is not repeated. So we'll have just x squared plus 1. And this is just on the sum over here, but I don't have enough room, so I'm moving it down here just to help out with spacing. Now again, the numerator needs to be 1 degree less than the denominator. Our denominator is x squared, so our numerator needs to be an x plus something term. So we have e x plus f here. And then we have this irreducible quadratic, but it's also repeated. So we need to make sure that we write this as many times as we have an exponent. X squared plus x plus 5 and x squared plus x plus 5 squared. Now again, just like before, these two would need to, if we were to add them together, if we were to add these two together, we would need to find a common denominator, which would be x squared plus x plus 5. We would have to multiply this one top and bottom by x squared plus x plus 5 in order to get a common denominator between these two, which is why we have to account for it. And we would, of course, have gx plus h plus ix plus j here. Because again, it needs to be 1 degree less than the denominator. And here, this is a quadratic inside the parentheses, so we do 1 degree less than a quadratic, which is a linear function. I'm going to add a little bit more here. What if we had then x squared as well? If we had an x squared, these are linear, the x terms. We would have something over x plus something over x squared. This is just like saying x minus 0 squared. So it will match the pattern of the x plus 2 cubed, where we have a j with this would be k, and this would be l. If you think about your x as x minus 0, you want to think of this as a linear factor. All right, that's going to be it for today. I will see you all in the next lecture.